So now that we have verified through part 1 of this exam via dimensional analysis that the Sherwood, Reynolds, and Schmidt numbers are the appropriate dimensionless groups to use for the given scenario, we now want to generate 100 pseudo-experimental data points from this given correlation, the Sherwood-Gilligan correlation, using a 10% normally distributed experimental error. And then after we have generated all of these data points, we're going to fit the data using the correlation form. Sherwood is equal to A times the Reynolds number to the B power times the Schmidt number to the C power, both by linear regression via the Penrose pseudo-inverse method, as well as minimizing the sum square error between the model and the data. After we have fit the data using these two methods, we want to plot the data on a 3D plot and fit a wireframe mesh grid to model the data. So in order to complete all of these steps, we first need to import a few tools into our Google Collaboratory Notebook to do this. So the first tool we need to import is NumPy, which is numerical Python, since we'll be working with numbers. And I'm going to abbreviate NumPy as NP, just so I don't have to type it out every time. After this, we know that we want to be able to minimize the sum square error. And SciPy has a function within the optimization toolbox called minimize, and this will help us do that. So from SciPy, in the optimize toolbox, so scipy.optimize, we're going to import the minimize function. Okay, after we do this, we want to create a figure to graph all of our points on. So we want to import the make subplots feature from Plotly. So from Plotly in the subplots toolkit, subplots, import make subplots. And this will help us set up our graph. And then after this, we want to be able to plot our points on our graph. So we need to import a tool called graph objects. So import plotly.graphObjects, graph objects, and I'm going to abbreviate this as GO, just so I don't have to write it out every time. And then finally, we want to be able to change the layout and the style of our plot. So I'm going to import plotly.io, which will allow us to change different features of our plots. Plotly, and I'm going to abbreviate this as PIO. And then this is a personal preference, but I prefer my graphs to have a dark background. I just think it looks a little bit better. So I'm going to change the default setting of Plotly from light to dark backgrounds. So I'm going to change the default. So pio.templates.default, and I'm going to set this equal to Plotly dark, and this will give us our dark background. Okay, hit Shift Enter, make sure everything runs all right and imports correctly. Okay, now that we have all of our tools inputted, we can move on to creating our pseudo-experimental data. So the first thing we need to do is create values of the Reynolds number. So it says that we want to generate 100 pseudo-experimental data points. So I'm going to use a function called, with a NumPy called random.uniform, and this will create a series of uniformly distributed data points within the given range. So I'm going to set the lower bound. We see that the Reynolds number is valid over the range of 2,000 to 35,000. So I'm going to set the lower bound equal to 2,000 and the upper bound equal to 35,000. and then we want 100 data points, so we'll put 100 right there. And for example, if we hit Shift Enter and run this cell, and then we type in the Reynolds number here, it gives us an array of 100 different data points for the Reynolds number within the bounds that we gave. So after this, we want to do the same thing with the Schmidt number. So np.random.uniform. And the bounds for this are different. So we're going to set the lower bound equal to 0.6 and the upper bound equal to 2.5. So 0.6, 2.5, and we want 100 data points for this as well. So now that we have these data points, we can calculate the Sherwood number using the Sherwood-Gilligan correlation. So I'm going to type in this relation that we are given. So the Sherwood number is equal to 0.023 times the Reynolds number raised to the 0.83 power, 0.83 times the Schmidt number raised to the 0.44 power. Now this would be fine if we did not need to account for any error, but since we need to account for error via a 10% normally distributed experimental error, I'm going to redefine the Sherwood number and set it equal to a numpy.random.normal, since we want normally distributed experimental error. And then I'm going to set the location equal to the Sherwood number because this expression is what we want to use to calculate it. And then we want to set the scale equal to 0.1 times the Sherwood number. And this is what will give us our 10% normally distributed experimental error. So after we do this, we type in Sherwood number. We can see that it calculates the Sherwood number featuring a 10% error using the Reynolds number and Schmidt numbers that we created. So after we do this, we can move on to fitting our data. And the first method that we're going to use to fit this data is linear regression featuring the Penrose pseudo-inverse method. So I'm going to move over to my whiteboard so that I can do some matrix manipulation to fit this data. So we're given that the Sherwood number is in this form. Sherwood number is equal to A times the A times the Reynolds number to the B power times the Schmidt number to the C power. Now in order to linearize this, we need to get all of the exponents out of the exponents. So we can take the natural log of each side of this equation, and we'll get the natural log of the Sherwood number is equal to the natural log of A plus B natural log of the Reynolds number plus C natural log of the Schmidt number. So what we want to determine is the intercept right here, and we can do this by creating a design matrix and multiplying it by the unknown matrix. The unknown matrix, when we solve for it, will give us our coefficients A, B, and C that we're looking for. So we want to create a design matrix that has 3 columns. The first column will be all ones, formatted the same way that the Sherwood numbers are. So this will hold the place of the Sherwood numbers. The second column will be the natural log of the Reynolds number, and this will be the natural log of all of the values that we created in the previous step. And then same goes, the third column is the natural log of all the Schmidt numbers. We want to multiply this by our matrix B. I called it B because it's the intercept of the equation, and this will give us our coefficients once we isolate it. And then finally, on the other side of the equation is the natural log of the Sherwood number. So this will be the natural log of all of the Sherwood numbers generated. So I'm going to call this design matrix X. So design matrix X times our unknown matrix B is equal to the matrix of the natural log of all the Sherwood numbers. And then the goal of this matrix manipulation is to isolate this unknown matrix B. So the first step in order to do this, we can multiply each side of the equation by the transpose of our design matrix X. So the transpose of a matrix is the matrix flipped over its diagonal, and when we multiply the transpose by the original matrix, we create a square matrix, and this will help us linearize and fit our data. So after we do this, we get that the X transpose times the X matrix times our unknown matrix B is equal to X transpose times the natural log of the Sherwood number. I'm going to zoom out a little bit really quick. And so after we get this, we still need to isolate our unknown matrix, and this is easily done by multiplying everything by the inverse of this X transpose times X. So multiplying everything by the inverse, we get X transpose times X inverse, and we get our unknown matrix B is equal to the inverse X transpose times X multiplied by our design matrix X, and then multiplied by the natural log of the Sherwood number matrix. Okay, so now that we have done this, I'm going to move this back over here, and we can create our design matrix in Google Cloud Laboratory. So I'm going to say X is equal to, NumPy has a function called column stack, and this will allow us to create a matrix out of all of the arrays of our, out of different arrays. So we column stack, and since it's a matrix, we need brackets, and our first column will be ones. So we want to format these ones to look like the Sherwood number since they're a placeholder. So numpy.oneslike, and this will allow us to format it to any form that we want. So we want to format it in the form of the Sherwood number. And then our second column will be the natural log of the Reynolds numbers. So this is numpy.log of the Reynolds number. And then finally, the third column is the log of the Schmidt number. Okay, so if we run this, ran smoothly, and if we type in X, it can see that it created a matrix out of our three different arrays. So we have ones in the first column, natural logs of the Reynolds number in the second, and the natural log of the Schmidt in the third. So after we have done this, we can solve for our unknown matrix B through some matrix multiplication. So matrix multiplication in Python, the multiplication signs are @ signs, and then NumPy also has a linear algebra function, which will allow us to take the inverse of our X transpose and X matrix. So X dot T times X, that's our first matrix, and then using @ signs to multiply. And then our second matrix is just X. Oh, so it should be X transpose, not just X. T times the natural log of the Sherwood number. So numpy dot log of the Sherwood number. So if we take this okay, so I forgot to put inverse after linear algebra, so inverse. Okay, so this should work now. And when we type in B, we are given an array of our coefficients. So we can see that our B is 0.81, which is very comparable to 0.83, and C is 0.46 and comparable to 0.44. But the A value is not comparable, and this is because this is the natural log of A, so we need to print this out and raise E to the A power. So print, and I'm going to print the first numpy.exponent B at 0. This will give us the actual value of A, and then I'll print this along with B at 1, which is the value of B, and then B at 2, which is the value of C. Okay. An extra parenthesis. Okay, so here we are given our values for A, B, and C, and they are very comparable to the values given in the Sherwood-Gilligan correlation. They are different because we simulated a 10% experimental error, and we have successfully fitted this data through linear regression. So now that we have done this, we want to move on to our second method of fitting the data, which is through minimizing the sum square error. So I'm first going to do this by defining a function. I'm going to call this sum square because that's what we're doing. And then any parameter, so I'm just going to do that P for parameter. And then we want to return numpy.sum of the square of this Sherwood-Gilligan correlation set equal to 0. So we want to set that equal to 0 and then square it, and we're going to take the sum of that. So we're going to do Sherwood minus 0.23, or minus the first value of the parameter, so P at 0, and this will be our A value, times the Reynolds number, raised to the parameter at 1, which is our B value, times the Schmidt number, raised to our C value, which is the parameter at 2. So we should run this, it runs fine. And then after we have found the sum of the square, we want to minimize this error. So we're going to use the minimize function. And then the parameters that are necessary for this are the function that we just defined, which is sum square, and then also our initial guesses for these values, which will just plug in the coefficients that we are given in the Sherwood-Gilligan correlation. So we want to minimize this data, so sum square, and then we're going to input our initial guesses as an array. So we're going to do 0.023, 0.83, and 0.44. So if we scroll down, this is not correct. Oh, I forgot to square this. So we need to square this whole thing. Okay, so if you run that again, there we go. We get an array down here in our X location, and it gives us the values of, it gives us the A, B, and C values for our Sherwood-Gilligan correlation, accounting for that 10% error. So we get 0.21, 0.83, and 0.50. So these are very close to the values that we get above. And I'm just going to store this into a variable. I'm just going to label it coefficient. And then we can access this data anytime. by saying coefficient.x, since the data was in the x field. So there it prints out our data again in an array format. So now that we have done all of this and we have fitted our data using the two methods, we need to move on to graphing our data.